PLA, polylactic acid. This is a plastic that's been around for many, many years. Back in the 60s, it was starting to be used a lot for sutures. If you had an operation, if you had a heart surgery, you got to have sutures on your heart. The last thing you want to do is have to reopen that patient to remove the sutures. Well, lactic acid is the same thing that you get in your legs when you've been running too long or exercising too much without drinking enough water, and you get your cramps. So your body is used to this chemistry in your body and is able to adjust to it. And so we polymerize that lactic acid into polylactic acid, and we have material that will degrade. Well, it wasn't until about 12, 15 years ago, NatureWorks figured out how to do this on a large scale. If you're making sutures, you're not using a lot of materials, but if I want to make water bottles or if I want to make pots out of this, I need to make this on a much larger scale. And so they came up with a chemical pathway that allowed them to produce this polylactic acid on large scale. And it has to do because polylactic acid is made with a process of removing the water, and once you do this, it can be self-defeating and it'll stop it. And they figured out a chemical pathway to solve this problem. When it first came out, they were talking about it being degradable, then they corrected the term and said it's compostable. And degradable and compostable are not the same thing. Compostability means that there's a particular environment, such as temperature and humidity. And PLA is compostable. It will break down if it's in a commercially set up composting bin. It has to be a relatively high temperature, has to have a relatively high moisture content, and it will break down in about 30 days, and it'll start to disappear. Now what happens to that carbon? We have to ask that question. Is it going into the earth? Is it going in the atmosphere? And so on. And there are ways to test that. The reason this takes a relatively long time to break down is there's two processes. First thing is that these long polymer chains have to be cut up through hydrolysis, the addition of water. Once they get down to a relatively small weight, then microbes can eat them. I think I may have some pictures of the microbes eating some of our stuff. And so if you look at, like, for example, molecular weight, or how long the polymer chains are as a function of time in a composting facility, you can see that it takes about 2 to 3 weeks to get down to something that's relatively small where microbes can then kick in and start eating it. So this is a disadvantage of this. When it's the sun chip bags, anybody remember that? The noisy, they were made out of PLA. And so that's another disadvantage of PLA. When you look at it, it's relatively brittle material compared to most of our petrochemical plastics. If you got a PLA cup and you drop it, it is likely to shatter. It is a brittle material. Now the other materials that are coming out of PHAs, PHBs, these have the advantage in that they come directly from microbes and they're already polymerized. PLA, I take cornstarch, a polymer, I chop it up, make it into sugar. I feed it to a microbe. Microbe gives me lactic acid. I re-polymerize it. I've done a lot of things. There's a lot of unit operations in that whole thing to get to polylactic acid from starch. I might be able to save some time and do it from corn sugar where you don't have to cut up my polysaccharide, my starch. I might be able to get there a little bit easier, but still I got a lot of processes. These materials have the advantage that they come directly out of microbes. Dr. Schrader indicated he was talking about that there are storage chemistry. So I can extract that. Now that's not necessarily so easy. A lot of these microbes, if they have a chemistry that's being used as energy storage, such as PHA and PHB, they don't want to give it up. It's like me. I don't want to give up my fat. It's hard for me to get rid of it. I got to exercise and eat right and all this other stuff. These guys are the same way. They don't want to give this up. This is energy storage. This is how they survive. But it does have the advantage that they break down faster. So if, for example, I'm looking at biodegradation as a function of time and days, so we've got 0 days and about 3 days. In a composting facility, it breaks down in about 3 or 4 days. But if I don't have that, it still breaks down in 3 to 4 days, maybe 5 or 6 days. I can break this down. So PHA, PHB have the advantage that the chemical pathways to get to the product is easier, and they degrade a little bit easier as well. These were the first 2 big pushes to make bioplastics. But what's really going on in industry right now, and Coca-Cola deserves a pat on the back, they have really spearheaded this technology. Coca-Cola has figured out a way to make PET, polyethylene terephthalate, at least partially out of renewable feedstock. So if you go and you pick up a Coca-Cola bottle, more than likely that bottle is going to say from renewable feedstock. It's not 100%, 1/3 by weight. The ethylene glycol that's used to make PET is from renewable feedstocks. The terphthalic acid, not yet, but they're working on it. And so there's a number up here, 12 billion. Anybody know what that number corresponds to? How many bottles Coca-Cola has manufactured to date? And that was back in October when I visited with them, so that numbers went up, I'm sure, a little bit. But Coca-Cola has made 12 billion bottles, whether it's drink bottles, I think that their product is Oasis, if I remember correctly, is Coca-Cola's water bottler, or from their carbonated beverages. 12 billion. That is enough bottles to wrap around the earth about 400 times. Right?
When did they start?
They've been working on this for many years. This is not a trivial exercise. So, you know, they have the infrastructure to set up, and they've been doing this directly. Now, they have teamed up with Heinz Ketchup. So if you go to, is it Giant Eagle? Is Giant Eagle still around here? When I left here, Giant Eagle and Kroger's were the two big. I mean, man, I am dropping all kind of trade names and being recorded, and man, I'm going to be in trouble. But Heinz Ketchup has teamed up with them and are now also making their bottles out of this renewable. But it's a 1-to-1 drop-in. 1-to-1 meaning that it's exactly like PET. It is PET on a chemical level, just that it's not radioactive. Well, at least 1/3 of it's not radioactive. It processes, it behaves exactly like PET. So now this thing can go right back into the recycle bin, even though it's at least partially and maybe in the future 100% renewable. So there's huge advantages to that. And so what they've done is last year it was announced that Coca-Cola, Ford Motor Company, Heinz, Nike, and Procter & Gamble have all collaborated together, and what they're going to do is get rid of this, and they're going to have a 100% bio-based PET plastic. And so it'll all come from that. The goal is to be away from feedstock that are used for food, right? When you drink, okay? So this is their goal, is to get to that. And I would like to point out, I have plagiarized this from Troy Industries. This is not my slide. I got that from Metabolics at one point, so I would like to point this out that this is not my slide. But that is their goal. Now there's another lady at Ford Motor Company, and we'll see if we can play this slide, maybe, real quickly.
That's a good question. We believe that it benefits the planet. The primary focus of my group has been developing biomaterials. And this is the biomaterials team. There are 5 women on the team, and most of us have children, and we'd like to see the planet cleaner. Green to me means a material that is sustainable. The vehicle has about 300 pounds of plastics on it. We're using natural fibers to reinforce plastic materials. The traditional materials can be 500 to 1,000 years in a landfill. All the plastic that is around you, we hope to replace with this material. It can be simply put into a compost pile and will degrade within 90 to 120 days. There were many people that told us that it wasn't possible to put even a minute amount of soy into the sea cushions. They said they tried it and said it could not be done. We now meet all the specifications for good automotive foam. Natural fiber composites are about 20% to 30% lighter than traditional glass-filled composites, which is great for fuel economy. I think it's very important to work on preserving the environment, and I think we need to do it now.
So the takeaway from this, between what Ford, Coca-Cola, and Nike are doing, is a strong indicator that bioplastics are here and they're here to stay. You know, every Ford car has at least some amount of biofoam in their seats, if not all of it, being polyurethane, soy-based polyurethane. And so this is going on. Now there are other things. I don't want to alleviate and say there's no other plastics are going on. You know, companies like Braskem is taking soybean oil or taking sugars and turning it into polyethylene and polypropylene. So there's other companies that are making big strides in this area. And it hasn't been that we haven't been doing this for a long time. Castor oil has been made, turned into polyurethanes for a long, long time. So, you know, there's other feedstocks that are out there, there's other companies, but these right now are kind of on my radar as real pioneers that are doing some really great stuff out there. Debbie, Dr. Molesky, she gave a talk at my kickoff meeting for the CB Squared NSF grant, and she did a great job. She was about in tears. I mean, she was really promoting that this is so important that we spearhead this technology and make sure that it moves forward. Now, when we make bioplastics, like any other plastic, what we need is pellets. When you go out and buy plastics, this is your common feedstock, is pellets. Primarily because it's the easy form to transport, and it also allows us to run it through an extruder. When you try to melt plastics, it's not an easy thing. Plastics have low thermal conductivity. So the way I melt these quickly is I heat them internally. And I heat them internally through shear heating, and I do that with an extruder. So I just run that through an extruder, I shear these pellets, and I can melt an enormous amount of plastic very quickly because I produce heat internally and I don't have to worry about this low thermal conductivity. Once I have molten plastic, I can shoot that into a mold. And so this is called injection molding. And this is one of the most common ways to make things. So we talked about that that's how these pots are manufactured, is with an injection molding process. Another way is vacuum thermoforming. In this case, I take the pellets, I extrude them into a sheet, and then I use infrared lamps and I heat that plastic up, and then I pull a vacuum. So in this case, that plastic starts out here, the vacuum pulls it down, more accurately atmospheric pressure pushes down onto that, and I can make a cup. Or I can make a tray. Those are the two most common ways that these type of products are going to be made, either with injection molding or with a vacuum thermoforming process. We've done a little bit of vacuum thermoforming on some of these materials, but the majority of our experience has been with injection molding. Now, this all starts out from a work. There's really two people responsible for why we're all sitting here in this room today. One is by the name of Matt Hilgeson. Matt was a graduate student under Dr. William Graves that came to my office about 5 years ago, and he knew I was making stuff out of plant protein, and he had this crazy idea about, hey, let's make pots out of it because they got nitrogen in them and they got all this other stuff that may help plants self-fertilize. Okay, fine. So we made some of them. So he is actually one of the people that really pioneered this work. And then the next person is this guy, Jim Schrader, sitting here. He's the next person who really wrote the big grant. Even though Bill Graves is the PI on the grant, it's actually Jim who actually spearheaded and made this all happen. But the idea was we take plant protein, which is polymerized amino acids, and turn them into pots.